So even though the logarithm is only defined as the inverse, that is, we don't have any series of basic arithmetic steps we can use to compute it. But even so, we can figure out some of its basic properties. And a lot of that comes from the fact that it is defined as an inverse. In particular, because it's the inverse of an exponential, the domain of a log function is going to be the same as the range of an exponential function. Remember, the range of an exponential was all the positive numbers, so the domain of the log function is going to be all the positive numbers. And again, because it's an inverse, the range of a log function is going to be the same as the domain of an exponential. And remember, the domain of an exponential was all real numbers. So, same story with the range of a log function. So the range of a log function will always be all real numbers. The domain consists of wherever the argument of the log is positive. So whatever's inside the log, that has to be positive. And the range will always be all real numbers. So if we meet a log function in the wild, the domain is wherever the argument, in this case 2x minus 5, is greater than 0. We solve that, add 5 to both sides, divide by 2. To solve that, we add 5 to both sides, so 2x is greater than 5. And then divide both sides by 2, so we get x is greater than 5 divided by 2, 5 halves. So the domain is the numbers 5 halves to infinity. And remember, we don't need to reverse that inequality because we divided by something positive. The range is easier. The range of a log function is always the same. It's always all real numbers. We don't need to do any work to find that. We just need to remember that that's always the range of a log function. Also, even though we don't have any basic arithmetic rules that let us compute them, we do know some basic values for logarithms. This works for any bases where the log is defined. So that means the base is a positive number and it's not equal to 1. So since for any number like that, that number to the 0 power is 1, switch the exponent and the argument, the log in any base of 1 is 0. Since any number to the first power is just that number, the log in any base of that number is 1. Because now our base is not 0, so we can take it to the negative first power. And any number to the negative first power is just the reciprocal of that number. So if we take the log of the reciprocal of the base, that's negative 1. And now this last statement is a really obvious fact because I'm just saying that something equals itself. Right? B to the n equals b to the n. But now, if I exchange the exponent and the argument, I get a new fact. The log base b of b to the n is always n. So even though we don't have any basic arithmetic steps we can use to find the log, there are certain numbers for which we know the log. So if we want to take, for example, the log base 4 of 1, well, that's just 0, because the log in any base of 1 is always 0. The log base 4 of 4 is 1, because the log in any base of the number itself is always 1. The log base 4 of 1/4, well, that's -1, because 1/4 is the reciprocal of 4. And the log base 4 of 4 to the 3/2, this is 8 if we worked it out. The log base 4 of 4 to the 3/2 is just 3/2. And there we go. So if we know what power of 4 the argument of our log is, then the log is just that, because the log is a function that tells us what power we need.